So I think we have around 50 minutes to 1 hour, right? So let's see how, how many topics we covered. So as I said in the abstract, so I'll be covering the topics which are kind of uh, concepts related with physics, space, or astronomy. And I will cover that from the point of view of virtual learning, how you can make things interactive. So it's not it doesn't become boring for students as well as teachers, when these concepts are being taught, especially in the virtual environment. So as I was told that most of the participating students are from grade 8 background. So I thought, let me go through your textbooks. And your textbook has a lot of interesting topics. As you can see, I have highlighted some physics topics and also topics related with space. So chapter number 19, it is all about life cycle of stars, very interesting. And then going to 9th standard, so you can see a transition that on 8th standard book, the title is general science, and then it shifts to science and technology. So I'm very happy with the syllabus designers who have included interesting topics. I wish I had that. I could have had that in my school times. And so here in the 9th standard, you can see again interesting topics such as observing space and telescopes. Then there is a reflection of light. Previously, it was refraction of light in the 8th standard. And of course, some basic physics topics. Then moving on to the 10th standard textbook, Science and Technology. Again, part 1, you are having space related topics such as gravitation and space missions. In fact, uh, I uh, I happened to meet my school teacher. It was then my school teacher just showed me this textbook, and she said, "See, now space topics have been introduced in the state board syllabus," and I was quite happy, excited to go through the content, and it was very delighting for me that topics such as gravitations and space missions have been included. And even not just our state board syllabus, but I have gone through the syllabus of other boards such as CBSE and ICSE and IB board. Even they are having very interesting topics which connect with space and technology. And the main reason behind this is, all we know that this fourth industrial revolution is dependent on the technology and space aspects. So you all are at right age where these things should be exposed to you, and that is how you will be inspired to take up your careers in the STEM fields. And the whole motivation behind Vipnet activity is to actually inculcate that interest. So in the same connection, we had this online workshop in May last year, where we introduce school level space and astronomy, how that can be introduced at school level. We had a teachers training workshop, followed by which even I gave a talk about introduction to space missions, which was mostly focused on the chapter number 10 in grade 10. And that is how it all started. So then coming back to our today's session, so I have chosen some of these topics focusing on your textbook content, and I hope you all will enjoy. So starting from very basic aspects of telescope. So we all know that the universe around us, let it be planets in our solar system, let it be stars, galaxies, black holes, or other parts of the universe which we are observing, all that we are observing is just by constructing such ground-based or space-based telescopes. Isn't it interesting that to measure the temperature of the sun, you don't have to carry a thermometer and insert it inside sun and then come back? All the information what we are actually gathering about the universe is actually through light. And telescope has been a backbone, be it a optical telescope, what some of you might have at home, and be it a radio telescope or X-ray telescope or ultraviolet telescope, be whatever telescope it is, all the information what we are learning, we are getting new insights on the universe, is all through the photons. And that is why I thought, let us start about telescope, how we can learn the basics of telescope through an interactive learning simulation. So here is a simulation. So before getting into the simulation, let me just quickly discuss the basic physics principles associated with the telescope and its function. So I'll start with the basic rules of laws of reflection and laws of refraction. Some of you must have already gone through them, but I'll still repeat for everyone. So if you are having an incident ray, so in the domain of geometric optics, we always think of light as a ray. So if there is a ray coming from a distant source, that ray travels in a medium which can be shown by a line with an arrow depicting the direction of the light ray. And that light ray, when is incident on an interface, now depending upon the properties of that interface and the properties of the medium having different densities, so the light, part of the light may get reflected or may fully get reflected, and then you are having the reflected ray. And the law of reflection states that the angle of reflection is equal to angle of incidence with respect to the normal, and normal is a straight line which is drawn perpendicular to the interface and the point at which the incident ray is incident on that interface. Then followed by the law of reflection of light, what we have here is law of refraction. Now the light not only gets reflected, but it can also get refracted. Only thing, as it undergoes refraction, there are certain changes. As you can see, the angle of refraction, which is again with respect to a normal, may not be always same as angle of incidence. In fact, the angle of refraction and incidence will be same only when the medium is same. So if you are having a change of medium, and by change of medium, I think of it is either a change in change in density, or even the constituents of that medium, which actually uh, result which results in the change in angle of refraction of light, because the velocity of light changes as the light goes from one medium to another medium. And because of that change in velocity, then followed by change in wavelength, of course the frequency stays same, and because of which uh, there is a different angle of refraction. So for example, here you are having air and water. So one is a rarer medium and another is a denser medium. So when light moves from a rarer medium to a denser medium, you will see that the refracted ray bends towards the normal. If it is the other way around, if the light is actually going from a denser medium to a rarer medium, in this case, you can reverse the direction of light. If the light ray is traveling from water and entering in air, the refracted ray will actually go away from the normal. So I think these are the basic facts I would like to discuss before jumping into the telescope. Then, based on these laws of reflection and refraction, then you go on to the next level of lenses. I think some of you might have already come across the functioning of lenses. So if I'm looking at how light interacts and propagates through a convex lens, and how then it undergoes refraction within the lens, and again it goes refraction while coming out of the lens. So how to predict, how to trace the ray of light. So again, this can be done in the domain of geometrical optics. And as you can see here, I'm just applying basic principles, what is shown in this diagram. So here, if there is a beam of parallel light, which is coming from the object at infinity, we always say in geometric optics that the parallel rays come from a source which is at infinity. So if there are set of parallel rays which are coming from the source, then you just focus on just one ray of light. It is arriving, it is incident at a point, again an interface which separates air and glass, of which the convex lens is made up of. And then you draw a normal at that point, and then you will see your ray is bending towards the normal. Am I correct?
Yes,
Is
sir.
everyone following what I'm saying?
Yes, sir.
Okay. So because the density is higher over here, so the velocity of light is slowing down, and in that case the ray after refraction is bending towards the normal. It then continues its straight line path, and again it gets incident at an interface separating glass and air. And now the ray is propagating from a denser medium to a rarer medium, and in that case it will refract away, it will bend away from the normal. And that is how one can actually trace the propagation of light ray through different materials using geometric optics. And it's just the extension of uh, these laws. Then you are having, when you go to 10th standard, I think even 9th standard, then you deal with the situations where there are objects placed at different distances. Then you can actually predict using geometrical optics what is going to be image look like, whether it is going to be inverted image or uh, real image, or the non-inverted image. So then similarly here I have a concave lens, and if I'm having a beam of parallel rays of light, so they tend to go away from the normal, and it just because of the shape of the concave lens following the basic principles of refraction. And then if you trace back these rays, your focal point is tend to be formed actually behind the lens. So I'll go to the next slide. Then coming to the telescope, what telescope offers us. So before getting into the various aspects of telescopes, let me deal with the basic parameters associated with telescope. For example, if you are going to buy a telescope, which are the technical specifications you must look at? So generally the technical description of telescope will have something like focal ratio, okay, the F number. So the focal ratio is actually defined as focal length upon aperture. And then you will also deal with the magnification, which is actually nothing but ratio of focal length of the telescope divided by the focal length of an eyepiece. So magnification gives you idea that actual object which you see through your eyes, how much times it is actually multiplied when you are looking at that object through a telescope. And then there are of course other aspects such as resolution, but I am not going into resolution in much depth. So then let us come to the telescope. Now imagine this is your virtual scene. You want to observe Jupiter through your telescope, and Jupiter is not at an infinite distance but a finite distance which is very large. So we will assume from the geometrical optics point of view that there are parallel rays reaching to the telescope, and these parallel rays after reflection, okay, we have already seen the laws of reflection, and then the concave mirror here will try to focus the parallel beam of light. And then just at the focus, you are having another concave mirror which will gather this light collected from the front end of the telescope, and it will further try to focus it. And again, at the focus placed at the optic axis, you are having a mirror which is placed at around 45 degrees angle, and which is kind of guiding those rays into the eyepiece. And this is how we actually see object through a telescope. So let me then go through go to the simulation. So I want the interaction, I want open interaction as I'm going through these simulations. Let me just give me a moment. So this is openly available simulation. I think you all should try at home, and it gives you the insight into the functioning of a telescope. Okay, so as you all can see, here is a telescope, and we are trying to look at the Jupiter, the way Galileo must have looked through his telescope when he first time made a telescope and looked at the moons of Jupiter, and he looked at the craters of moon. So as you can see, there are lot of parameters you all can see, right? All of you, can you see my
Yes,
screen?
sir.
So there are parameters such as primary diameter, primary focal ratio, and eyepiece focal length. So we'll just see step by step how these parameters actually affect your viewing. So so this is for a telescope with a diameter of 10 centimeter. That is this diameter. Then you are having a primary focal ratio. I already spoke about the focal ratio, how to calculate in the slide. And then you are having an eyepiece. Again, eyepiece will also have its focal length. So initially with the primary diameter of 10 centimeter, primary focal ratio 2, and eyepiece focal length 1 centimeter, let us see how the image looks like. So here are your beams, they get reflected and then they come to your eyepiece. So this is what a Jupiter will look like. Okay, again, these are don't expect that image. This is what actually the image will look like, but this is just to make you understand the role of these different parameters related with a Cassegrain or even a Newtonian reflector telescope. So now let me change the primary diameter. Let me change it to, let's say, 20 centimeter, 15 centimeter. Okay. Then let us look at things. Let us look at Jupiter again. What do you see? Okay. 15 centimeter. I'll move it to 25 centimeters. Okay. I want you all to observe.
So the Jupiter becomes bigger, like so magnification increases.
Slightly, but apart from that, anything else do you observe? Okay, I'll again go back to diameter 10 centimeter. Yes, your observation is good, but let me cover some
Sir,
other
I think
aspects.
the Jupiter, you are increasing the centimeters, the Jupiter is getting more bigger.
Yeah, that is correct. That is true. But can you look at the background stars actually?
Yes, sir.
Yes, sir. They are
So
getting
what is
lowered.
happening to those background stars? So as
They're
I'm
getting
They are
blurred.
being
increasing the
focused.
diameter of the telescope, you know, the background stars are become, you are able to resolve them properly. So this is what a brief idea I want to give you about the resolution. So it is something like you are trying to collect the raindrops during a rain, and how will you able to collect large amount of water? You will of course use a bucket with a larger diameter, right?
Yes.
Correct. So it's the same principle over here. So more is the diameter of my telescope, the more photons from that distant object are able to enter into the telescope, and that is why I am able to gather more information, and that actually leads to the picture is having more resolution, you can clearly see the images. That has got to do something with a resolution. Okay.
Yes, sir.
And let's keep now the diameter fixed, and I'm going to change the eyepiece. I'm going to change the eyepiece of the telescope. Previously it was 1 centimeter. Let me now make it 2 centimeter. Let us see what happens. What happened? Can anyone mention? Can anyone?
Jupiter's size has, we can
Sir,
see
more the
smaller
photons from the
Jupiter.
background came to our eyepiece even, and
Yeah.
Jupiter's become small.
So as I had shown you the slide talking about the magnification, now if I'm reducing my focal length of eyepiece, okay, what am I actually doing?
Increasing the
I'm increasing the focal length of an eyepiece. Okay, so actually I'm decreasing the magnification. Am I correct?
Yes, yes, sir.
So keeping focal length of the telescope fixed, I am actually now varying the focal length of eyepiece. And in our case, I have actually increased the focal length of eyepiece. So if I'm increasing my denominator and keeping numerator constant, I'm actually decreasing the magnification factor. And that is what exactly you are able to see in this simulation. So sometimes when you are actually observing the night sky, it's not just you are interested in the object at the center, but you might want to see the larger field of view, or you might be interested to see a nebula which is having comparatively a larger diameter as compared to a Jupiter, the angular diameter of Jupiter. And in that case, then you would prefer to use eyepiece with a larger focal length, because that allows you to look at the larger field of view in the night sky. So is this aspect clear to everyone?
yes, sir.
Okay.
Yes.
So then let us look at the primary focal ratio. If I'm changing the primary focal ratio, what should we expect? So as you can see here, by increasing the primary focal ratio, do you observe any change in the telescope? What do you observe? So here again, I'll go back to the definition of the focal ratio, which is actually the focal length of the telescope upon the aperture. So what do you expect?
The aperture is constant, so sir, the focal length of telescope is getting changed.
The position is getting changed.
Okay, so that I give you as a take-home exercise, so you can go through this simulation. Of course, I'll share all these links, and you go through, play with these parameters, and then come up with your interpretation and do some literature review. Okay, so let's go ahead. Just give me a moment. Are you all able to see my screen?
Yes, sir.
Okay. Yeah. Going next. So we saw the basic functioning of telescope, but then the next level is, so as you all know that we are human beings are curious, always curious to know about their existence. And we have been pursuing our curiosity about our own existence in the universe, where we stand in the universe, whether there is a life which exists beyond Earth. And though it, even a Stone Age man, when he must have looked at the night sky, I think he must have also, that question must have come in his mind, that who is he and where is his position in the universe. And with a biological evolution now, where we are in the stage where we call ourselves Homo sapiens sapiens, and that curiosity we are still continuing with, and that has actually resulted in our technological and space endeavors, which has resulted in some of these missions which actually pursue that thought, that curiosity of human mind. So in this interactive simulation, we are going to discuss about exoplanet exploration. And I have taken a screenshot from NASA's exoplanet exploration website. And at the bottom of the slide, I have also given the link. So after this session, all of you can go through uh, uh, these web links. So as it is stated, that whether life exists beyond Earth is one of the most profound questions of all time. The answer will change us forever, whether it reveals a universe rich with life, one in which the life is rare and fragile, or even a universe in which we can find no other life at all. So both outcomes will be very interesting. So are we just a single planet on, are we just whether the life has evolved on just Earth, revolving around the sun in the entire universe, or even the life is, the universe, our whole universe is actually rich with life. The both outcomes will be very interesting to know. But even to come across, to finalize, or even to come to a conclusion with these two outcomes, we need to carry out deep research. And for that deep research, to look for the life in the universe, there have been missions like Kepler, TESS, and recently you must have heard about news of launching of James Webb Space Telescope, which is having a largest mirror. And in fact, I know on 19th of April, there is going to be a talk on James Webb Space Telescope. And even another telescope will be launched. And all these telescopes, one of their core functionality is going to look at, to understand whether there is a life beyond Earth. So how we are going to find the life beyond Earth? Let's look at that. So before getting into the detection technique of finding the life on other planets, these are called as exoplanets. So we always try to compare life, what we have observed on Earth. And as we know that our solar system is actually the system of the whole configuration of planets which are revolving around in a circular or elliptical orbit around sun. And the life which has evolved on Earth, it wouldn't have evolved if Earth, if it is very close to the sun, or if it is is away from the sun. So any planet which has to harbor life should be at such a distance which allows, which is actually favoring the life on that planet. So that is called as habitable zone. And it is also known as Goldilocks zone, where based on what type of star it is, and we can actually determine the habitable zone around that star, where if there is a planet in that zone which is revolving around the sun, there is a probability that life can exist on that planet. Going to the next slide. So again, if any of you have come across this news of discovery of TRAPPIST-1 system, again, it's the planetary system like us, but again, the difference is the star at the center is not like our sun. It is quite uh, I think it's a red dwarf star, and that actually changes the range of this Goldilocks zone. So if you're for sun-like system, the range for the Goldilocks zone is quite away from the sun, whereas if there is a star like a red dwarf star, the Goldilocks zone, its range is quite closer to the star, and accordingly, the overall radial range will also differ. So these are the different kind of stars we have in our universe. So the example at the bottom is sun-like star, and this sun-like star having a typical lifetime of 10 billion years. If this is a Goldilocks zone, then I go to another kind of star which is having a lifetime of 40 billion years, and with that kind of star you can see the Goldilocks zone is actually narrowing, it is actually getting narrowed, and as it gets narrowed, and if there is a planet in that Goldilocks zone, the first column is actually giving you idea about the radiation that planet is exposed to. So typically the X-ray radiance. So from our solar system's perspective, the kind of X-ray irradiance we have from our sun, and if that Goldilocks zone is actually further narrowed down for any other star, the X-ray irradiance increases by 25 times. And then if you're having again the another kind of star, okay, which is having 100 star with the lifetime of 100 billion years, and which further narrow downs the Goldilocks zone, its X-ray irradiance goes up by 100 times. So temperature wise, though situation might be favorable, but the X-ray irradiance wise, one has to understand whether the life can such planet can harbor life. So how do we go about detecting such exoplanets? So all of you must have heard about the planetary transits. Have you all heard of transit of Venus or transit of Mercury? Have you all heard of?
No, sir.
Okay. So transit is a phenomenon, especially it occurs in a planet which are, suppose if I'm talking about Earth, and with respect to Earth, my inner planets are Mercury and Venus, right? So there will be always a situation as you are moving from Earth towards the sun. So inner planets like Mercury or Venus, they will appear to pass over the sun's disk. They are actually not on the surface of the sun, but it just the way our grazing angle is towards the sun, it all depends upon that. So since the orbital planes of these planets, such as Mercury and Venus, are not very inclined with respect to the orbital planes of Earth and Sun, so this there is always a possibility that Sun and inner planet, either Mercury or Venus and Earth, they will all come in a straight line, and then you will able to see the small planet which is appear to move across the sun's disk. So this is called as a transit. Okay. So instead of a planet, if it is a moon, then we always come across situations such as eclipses. So if moon is covering the sun, because moon is moon is very closer to Earth, so the moon is able to apparently cover the sun's disk. The moon is very small, compared to sun. But since it is closer to Earth, it apparently blocks the sun, and that is how the eclipses occur, right?
Yes.
So when there is no moon, but there is a planet, we call it as a transit. Okay, because that planet is apparently not able to cover the complete disk of the sun. Now, with this kind of transit method of inner planets, the same situations might also arise if I am looking at any external solar systems in our universe, because even there is a central star, then there is a whole there are a set of planets which are revolving around that star. And if I'm looking at such exosolar systems, and if the orbital planes of such exoplanar exosolar systems, if they are somewhat parallel to our plane of observation, then there is a possibility that we can detect planets around that star. So imagine you're looking at a very distant star, but by observing very small fluctuations in that star, in which those fluctuations are occurring because actually the planet is moving around that star, and it is slightly able to block the light coming from that star, and you are actually observing that blocking of light, starlight, through a telescope. Are you able to understand what I'm saying? The way to detect exoplanet? Are you all following?
Yes, sir.
Okay. So how we actually detect these exoplanets? So as you can see, here is an exoplanet revolving around its star. And there are situations in which, so these situations are numbered, as you can see. So when it is at number 3, it is actually blocking the starlight, though in a very minute, so you can actually see a very minute fluctuation in the star's brightness. So there is 100%. So when it is not blocking the star, I am actually observing the starlight, which is with the 100% brightness. And when it starts covering the star's disk, the brightness starts reducing, and that reduction is not very large, not very significant, but just around max to max, it can just reduce to 99.5%. Now, you must be wondering how I am able to detect very small fluctuations in the star's light. But that is what the credit goes to the technology, because today's technology can produce very sensitive sensors, very sensitive cameras, which can detect not just a fluctuation of 0.5%, but even less than that. And with such technology at our hand, we can make this technology useful for detecting such exoplanets orbiting around stars. And this is simple method of detection with advanced technology can help us to locate, to even discover exoplanets which are revolving around stars. Otherwise, with just a telescope, ground-based telescope, looking at a star, you will not able to uh, discover if there is any planet revolving around that star. So in the next stage, one can actually detect the atmosphere of such exoplanet revolving around its star. So this slide simply shows a schematic, how we can determine if the planet is having an atmosphere, and if it has atmosphere, we can even estimate the composition of that atmosphere. So as you could see in this slide, that when the planet was at position 2, you are actually able to, your telescope is actually gathering light from the star as well as the planet. So if I am collecting the light by looking at this star, of course I don't know that there is a planet. Only after this, knowing that there is a dip in the starlight, we can conclude that there is an exoplanet. Now we have concluded that there is an exoplanet. Then researchers look at whether that planet is having an atmosphere, because just locating an exoplanet is not enough to conclude that there might be a possibility of life on that planet, but that planet should also have an atmosphere. But how we will detect atmosphere? So here is a procedure. So when the planet is not blocking that star, you are actually gathering the light coming from the star and also the light coming from that planet. And then as that planet, exoplanet, is revolving around the star, there is a possibility that it goes behind the star, right? And when it is behind the star, you are not able to collect the light from that planet. What you're actually collecting is a starlight, and by actually subtracting the pure starlight from the combined spectrum, one can actually obtain information about the atmosphere of that planet. I can hear some sound in the background.
अचानक पता नहीं क्यों मेरे जहन में उसका जवाब ये आया. मैंने कहा लता मंगेशकर से.
Excuse me, if you could mute your mic.
मैंने ये कहा कभी आपने लता मंगेशकर को गाते हुए सुना?
Okay, thank you. So knowing the position of exoplanet revolving around star and gathering the light at different positions, one can obtain the information about the atmosphere, whether that planet is having an atmosphere. And once such spectrum is obtained, from looking at that spectrum, one can even find what kind of composition exists for that planet atmosphere. Okay, so with that, I'll go. As I have already covered the detection principle, one of the detection principles for finding an exoplanet around a star. So let's look at the simulation. I'll go back to the simulation. So again, this is freely available simulation. You should try on your own. So as you could see, the exoplanet had just appeared to touch the star's disk, and you can see that there is apparent change in the brightness of the star, right? Can all of you see that?
Yes, sir.
Okay, then I move on to the next stage, where the exoplanet is nearly at the center of the star's disk, and you will see that the apparent change in the brightness is maximum. There is a dip, there is a maximum, it is at the maximum dip. There is a maximum dip in the starlight, and then as it again starts leaving the star's disk, the brightness again starts increasing. Okay, and that is how. So so it is always possible that star may not just have one planet revolving around it. A star can have multiple planets revolving around it, and so your dips can always have a combination. So as I am showing here just one planet, so there is always a possibility that you can have more than one exoplanets, and then the depending upon the combination will actually determine the depth of your apparent change in the brightness, the decrease in the brightness. And by analyzing such data from distant stars, one can discover multiple planets revolving around stars. And if you are periodically observing the dip in the brightness. So, and as we have learned about the circular motion around a star, that it is a periodic motion, then I can easily determine period of that exoplanet. And if I know period of that exoplanet, and again by some techniques I know the mass of the star, I can also determine at what distance that exoplanet is revolving around that star. And that is how these other worlds with exoplanets are being explored these days using these advanced telescopes. So all of you should try. There are other simulations also available on this web page. You should definitely give a try. So moving on to the next simulation. How much time do I have?
You can take 10 minutes more, 10.
Okay, I have more stuff to show. So okay. So all of you like playing games, computer games. So here is an interesting Explore Mars game. I have again shared the website at the bottom. And on April 16, 2021, there was this historic flight of Ingenuity helicopter of NASA's Perseverance mission. The helicopter took off with its first flight, which actually, this flight was tested on April 16, which actually also marks the 154th birth anniversary of the first Wright brothers flight. And both are historic moments for us, because following these historic moments, there we have seen the technological progress and how that technological progress has contributed in our overall socio-economic development around us. So maybe in future upcoming years, when humans they settle on Mars, this moment of test flight will actually mark a significant moment in the human settlement on Mars, where we might have the huge helicopters using which humans will go from one location to another location on Mars. Coming to the different aspects about fun facts about Mars. So the Mars is having very thin atmosphere as compared to Earth. And that is why when you are going to have a landing mission on Mars, you need to construct your parachute such a way that they are larger and they are able to create enough drag to actually, in a given span, it can substantially reduce the spacecraft's velocity. And coming to the mass of Mars, the mass of Mars is quite around 1/10 of that of Earth. So one can even estimate the acceleration due to gravity. That also is smaller as compared to Earth. And about the interior of Earth, the way we know about Earth and its interior through the decades of studies, we don't know much about the interior of Mars. And though some studies have been done, but very few missions have been sent. And this is one of the interesting mission on Mars, which is the InSight Mars mission, which is a scientific mission devoted to study the interior of Mars. So the mission carries a seismometer, and it carries a sensor which can measure the thermal conductivity at certain depth. And so this is not a rover, it just fixed, and it has actually placed its instruments, and it keeps monitoring the seismic activities on Mars and thermal conductivity, and there are other onboard instruments as well. And there have been many missions by different countries, and as you can see, the India is also not behind. We had our own Mangalyaan mission, in which it was a maiden attempt. We had a successful orbiter orbiting around Mars. Not all the countries in their very first attempt, they had a success. So we should be proud of our Mangalyaan mission. And last year, 2020, was very interesting because we had 3 Mars missions. So it was NASA's Perseverance rover and Ingenuity helicopter. That was one of the mission. Then United Arab Emirates, its agency launched the Hope orbiter mission. And then even Chinese space agency had their orbiter, lander, and a rover. All 3 missions were successful. And then coming to the rover aspect, why am I discussing this rover game? So many of you must be having wireless cars at home, toy cars, and it's not always exciting to run the car the way we want, but the same way we cannot follow when you are actually operating a rover, because there is whole aspect of power management, how you can efficiently use the onboard battery on the Mars rover, and with that power management, how efficiently you can scan the Martian surface. So this game will actually give you some insights of effectively choosing the steps. So as you can see that there is a virtual Mars surface and there are different sites to be analyzed. And you can actually give different steps to the Mars rover, and such as rotating with certain angles, then moving ahead. And then if you have to examine that particular rock, you can you can examine that rock after reaching to that location. And with the limited steps, how efficiently you can examine most of such sites on the Martian surface. So in your recess time or in interactive classroom sessions, you can always have these games, and these games will not only entertain you, but they will also give you some insights of how the overall rover management is actually decided, how you can effectively design a program on a Mars rover which helps you to analyze these rocks and execute your tasks. So as I mentioned in my previous point, that last year was very year 2020 was very interesting because it was having 3 Mars missions. So then you must have thought, why only certain years are in which the Mars missions are launched? So there is actually a launch window for launching missions to Mars, because before going, I think I'll skip this slide, the nature of orbits. I think you all know, and you can also study since we are having less time. So why we are having a specific launch window to such interplanetary mission? Because first of all, we have any space mission is having its own budget, and there is always a constraint on using fuel. So more is the fuel, leads to increase in the overall mass of the whole spacecraft. And then there is a constraint on how much actual payloads, their mass, sensors, how those should be incorporated in that mission. So you want to have, if you are designing interplanetary mission, you want to design your mission in such a way that you want to have a very good instrument carrying all types of sensors. So there has to be a proper balance between the fuel and the rover or any orbiter it carries. And so these missions are designed in such a way that you don't end up spending lot of money on fuel. So then how these missions are actually launched? So coming to our own Mars orbiter mission by Indian Space Research Organization. So all of you must have even seen the movie Mission Mangal, in which they have shown in very simple manner that how PSLV was actually launched. Instead of directly sending you can always have a rocket carrying more fuel, having more fuel capacity, which can be directly headed towards Mars. But then there are a lot of constraints. So one can always have a technique which is known as gravitational slingshot, where step by step you can increase the orbit of the rocket, and then comes a situation where it actually escapes the Earth's gravitational influence. That is called as the uh, transfer trajectory. And with that transfer trajectory, then there comes a point where the trajectory of the spacecraft intersects with the trajectory of Mars. And for all this to have, you need to have very good understanding of the trajectories of Earth, Mars, and actually maneuvering the spacecraft orbit. So that subject is called as astrodynamics. So again, I'll skip this slide. Again, let me go ahead. So this is the basic aspect of a circular orbit. And with any orbit, you are having a potential energy and kinetic energy. And by changing the kinetic energy, you can deal with different kinds of orbits. And that is how here it happens that I am changing my kinetic energy in step-by-step manner. And I can have an elongated orbit, and after elongated orbit, I can further increase the orbit such that it escapes the Earth's gravitational influence. And then I lower the orbit of the spacecraft such that its kinetic energy is decreased step by step, and then it has a bound orbit around Mars. So I'll go to simulation. Yeah.
If the spacecraft leaves Earth at just the right speed.
So as you can see, you can in the simulation that you're having the inner planets, Earth, and our neighbor Mars. And there is actually a launch date. So you can choose any launch date which is available in the simulation. And then let's just take any random date and see what happens. So here is your spacecraft launched from Earth, and it is on its way to reach Mars orbit. But then what happens? Does it reach Mars? What you all see?
No, sir.
It has not reached
Spacecraft
Mars,
lost
right? It
because
has
it
reached
doesn't get
Mars orbit, but it is not able to have the rendezvous with Mars. There is no bound orbit with Mars. So our spacecraft is lost. So now what to do? So in the simulation, of course, you can play with different dates and years and then find out the favorable condition. So I'm just going to take one simple favorable condition. Let me go to March 13. I'll go to the year 2016. And what you see in the picture? Can anyone comment? The Earth and Mars are like relatively
Sir,
closer. Relatively closer. So this is a situation kind of prior to a situation or where you can have always the Earth on whose one extreme sides there is Sun and there is Mars. So there is this is called as opposition, where you are having the Mars which is on the one side, you are having the Sun on the opposite side, the Earth is in between. And these situations, planetary situations, are advantageous, and they the time around such oppositions is actually favorable for launching space missions. So we'll see now what happens in the simulation. So here is your spacecraft launched from Earth. Yeah, and then the launch is successful. the spacecraft is actually captured by Mars, and if it is an orbiter, it has started orbiting around Mars. If it is a rover, then uh, it has to go even uh, further steps to land on Mars. So let's say if I change my launch date, let's say 11 March 2016, and see what happens. Spacecraft is lost. So as you can see from this simulation, that there is always a limited time window. So if you miss that time window, then you may not able to reach Mars, because you have the limited supply of fuel, and even if there are any maneuvers required between along the, because as you are seeing in this simulation, the trajectory is not always that simple. You might always require different kinds of maneuvers to actually such that the spacecraft follows that particular course which is designed by engineers. So you require onboard fuel, so there is always a complex calculation involved. You need to have some buffer fuel. You don't want to end up spending it during the launch. So considering all these aspects, you are dealing with a limited time window during which you have to launch any mission to Mars. I'll go to the next slide. So all of you know about this man. This man doesn't need any introduction. Elon Musk, who is doing revolutionary things in space with his reusable spacecrafts, space rockets. And we are going now to do something about rockets. And even India had its own space and nuclear program, started in a humble manner. And in fact, very first sounding rocket was launched from Thumba, and it was launched with the help from a local village church. They actually provided us a space, and that is how we actually the whole rocket was assembled in that church premises, and then it was launched on 21st November 1963, and the history of Indian space program was created. So India, uh, Dr. Vikram Sarabhai and Dr. Homi Baba, they are we quite owe to them, because they have played a significant role in setting up country's nuclear program and country's space program. And here you can see Dr. APJ Abdul Kalam. He is helping Arava Mudan, another team member that time, to while assembling a rocket. And you can see in a very humble manner the way we actually started our space program. So each country is having their own space program, and all these space programs requires development of rockets. And over the time, there have been significant developments in the construction of rockets, their design, the technology, the electronics, fuel systems. And you can see the highlighted rockets, which are from the Indian rockets. And then you can also see a highlighted rocket, which is being built by Elon Musk, which will take us to Mars. So India had its own history of rockets. So the previous slides which I showed, we had very our first flight, and since then till now we are having our own cryogenic rocket called a GSLV Mark III, and which will be helpful for interplanetary space missions. So coming to the basic principles of rocket. So the rocket requires a fuel, and that fuel has to be burnt. It has to be, there has to be a combustion of fuel. So to have that combustion, you need an oxidizer. So inside a rocket, you have a mechanism which, a controlled mechanism which mixes fuel with the oxidizer, and then a controlled combustion takes place. And because of this combustion, you are having the exhaust of gases, and these exhaust of gases are providing thrust to the rocket. This is the basic principle behind the rocket and generating a thrust. And that thrust actually helps us to carry the spacecraft from ground to a desired orbit, or even interplanetary space mission. So basic aspects of force. So what is a force? So the force is a push or a pull acting on an object due to its interaction with another object, and which actually changes the state of rest or uniform motion of that object. And that is how we define force in physics. So as per the Newton's second law, the definition of force is mass into acceleration. And we deal with different kinds of forces in our daily lives: frictional force, gravitational force, the force which mechanically we apply on objects. Then there is a drag force which opposes the motion of any object moving through air. And then you have a normal force which arises because there are two bodies in contact, and which is perpendicular to the surface on which body is kept. You are having a magnetic force, you are having electric force, then you are having a spring force. And these forces are further classified into the forces such as contact forces and non-contact forces. So the contact forces will always involve that the objects are in contact with each other, be it if you're pushing a box, you have kept a book on the table, or you are actually pulling a spring because you are attached a weight to that spring. And be for non-contact forces, like you have dealt with the bar magnets, how bar magnets can attract another bar magnet or repel a gravitational force or electrostatic force. So these are non-contact type of forces. Why I'm discussing these forces? Because in the simulation, what we deal with, some of these forces are involved. And while learning about these simulations, we need to have basic idea about types of forces. So this is my second last simulation, after which we can stop. I think somebody's mic is muted. You could mute the mic. Yeah. So here is a simulation, simple simulation. So you have a rocket mass, you have a rocket burn time, which you can always change from 1.1 seconds to 1.5 seconds. You also have, you can also change the rocket thrust. And so let's have the rocket mass. So let's keep these parameters as they are, and let us see what happens. So can anyone describe the motion? So we are having two graphs. One is the graph of velocity versus time, and another is graph of altitude versus time. Can
Sir,
anyone describe the motion?
Sir, in the velocity time graph, sir, we can see that when we apply, when the fuel is burned, sir, the speed, the velocity increases with time. But
Right.
as soon as the fuel finishes up, or we can say,
Right.
run out, sir, then the gravitational force actually works opposite to it and lowers down the velocity.
Correct. So then let's see if we increase the mass, what happens. Does it even go? Does it even fly higher? No, it doesn't, right?
No, sir.
Yeah.
Because the rocket thrust.
So the thrust is not enough. You need to have more rocket burn time. So in your virtual classroom scenario, you can always take different scenarios of rocket mass and rocket burn time and rocket thrust to see how does it affect the rocket velocity. So this is very crude, very simple simulation. But what I'm going to show you all is slightly more advanced simulation, which is actually used by amateur rocket makers. So in abroad, there are a lot of amateur groups which they actually create these small rockets. They even conduct these rocketry competitions. Different groups across the world take part in these rocketry competitions. And to design such these rockets, you need to understand in advance how the rocket can actually fly in space. And here is such a, again, slightly advanced simulation, but it gives you idea if you want to design your own rocket. So let me go to a single engine rocket simulator. Okay, so let's give the name to our rocket, Iwsa Vipnet. Okay, and I have some rocket mass. Let everything just keep things as they are. And here you will see the rocket engine type. So you have different kinds of engines which are actually the commercial standards which people use in standard rocketry. So let's take a standard engine, Aerotech E62, and uh, to these rockets, these are recoverable rockets because these rockets are carrying payload. So you need to have a parachute because once we run out of fuel, we need to actually recover the rocket module, rocket payload. So one has to accordingly design the parachute. You need to have some idea what kind of drag forces your rocket may experience in the atmosphere. And based on that, instead of actually firing the rocket, it is always better to understand how the rocket trajectory will turn out to be through a simulation. So let's run a simulation and see what do we get. So as you can see here, you are having different columns of time, drag force, thrust. Then there is a net force. Then there is mass, acceleration, velocity, altitude, area, velocity, and air density. And you can see the overall profile of the rocket over here, showing the peak altitude and peak velocity. And one can always note down these readings and you can have your own plot of all these parameters, how they change with time. So if you have a drag force, how the drag force changes as a function of time. Okay, so as you can see here, the drag force initially is smaller because your engine is on, your fuel is burning, and when you are controlling your slowly when the your engine stops functioning, your fuel is less fuel in the tank, your drag force will start increasing. And when you open a parachute, of course the drag force will be the highest and then it starts landing. So you can always see even here the mass, how the mass changes as a function of time because you are losing fuel with time. So in principle, the effective mass of the rocket should also change with time and acceleration. You can, so for different kinds of, so if I increase the rocket diameter, let me make it 0.5. Let me call it test rocket 2. And let me again fire it. What do you see? You see a completely different trajectory. So with these openly available tools, the students can always learn more about space and astronomy. And I feel I have more activities, but I won't go because of the restriction on time. But I feel that in my today's talk, I have given you a gist of activities and how one can learn about space and astronomy in a virtual scenario with the help of these interactive simulations. And with that, I say thank you. And I hope with this talk, I have encouraged you. And the platform is open for any question and answer.
Sure.
Hello, can you all hear me?
Yes, sir.
Yeah.
Sir, I had a general doubt, sir,
Yeah.
regarding. Sir, why are the orbits of planets not circular, sir? Because in the Newtonian gravity, sir, we can see